Good morning. I am Dr. R. Murali, Professor, Department of Mathematics, Dr. Ambedkar Institute of Technology, Bangalore. The sessions I am delivering is based on Engineering Mathematics 2, MA21, and I am delivering the lectures in module 3 related to partial differential equations. Now, in the previous sessions, we have understood what is a partial differential equation or PDE, how to form a PDE by the elimination of arbitrary constants in a given relation. A relation is given to you. By differentiating partially the given relation, you form the PDE. Then, how to form a PDE? By the elimination of arbitrary functions in a given relation. We have seen examples illustrating the elimination of 1 and 2 functions. You have seen that if you eliminate one function, you get a PDE of order 1. And 2 functions gives you a PDE of order 2. Now, in today's session, we will be more specific. We will look into 2 types of expressions given. So, we try to form a PDE by the elimination of one arbitrary function, say f from a given relation, when the relation is in the form u equal to f of v. U and v are some functions of x, y, z, and second f of u comma v equal to 0. Okay, we can see later that both are equivalent, but the methods of formation of the PDE are entirely different. Now, let us recollect the following from our earlier sessions. As you know, friends, partial differential equations can be formed by 2 methods. One, by the elimination of arbitrary constants from a given relation, and the second, by the elimination of arbitrary functions from a given relation. Now, we have solved examples in this type in our first session in PDE. In the case of arbitrary constants, if the number of arbitrary constants is equal to the number of independent variables present in the given relation, we have seen that you obtain a PDE of order 1. Whereas, if the number of constants is more than the number of independent variables, it so happens that the PDE will be of order 2 and higher. Whereas, in the case of arbitrary functions, the order of the PDE is equal to the number of functions eliminated. That is to say, you eliminate one function, you get a PDE of order 1. 2 functions, you obtain a PDE of order 2. Now, the case where we eliminate 2 functions or one function is already discussed in our previous session. And you must note that when arbitrary functions are eliminated, constants, if present, need not be removed from the relation. They can be present in the final PDE also. Now, these are the notations we have been following right from the first session. We consider z to be a function of 2 independent variables x and y. So, z is the dependent variable which depends on the variables x and y. The first order derivative dou z by dou x, which is also denoted by zx, is denoted by p. The first order derivative dou z by dou y, which is also denoted by zy, is q. Then, for the second order derivatives, dou square z by dou x square, which is zxx, is denoted by r. Then, dou square z by dou x dou y, which is by notation zxy, and as you know, friends, it is also the same as dou square z by dou y dou x, dou y dou x. So, dou square z by dou y dou x, which is z y x, that is equal to s. Notice that it is immaterial how you differentiate. In dou square z by dou x dou y, you have x and y, whereas in dou square z by dou y dou x, you have y and x. So, which is z y x, that is denoted by s. And finally, dou square z by dou y square, which is z y y equal to t. Now, we have seen that a PDE containing P and Q is a PDE of order 1, whereas a PDE containing one or more of the partial derivatives r, s or t is a PDE of order 2. Now, we have in the previous sessions we have seen examples related to the elimination of arbitrary functions. Now, in today's session we will be more specific. As I said earlier, we will consider two relations. First, a relation in the form u equal to f of v, where u and v are functions of x, y and z. Notice that even though u, v are functions of x, y, z, z is the dependent variable which depends on x and y. Now, what is the aim? The aim is to eliminate the function f, because we are eliminating only one function, that will result in a PDE of order 1, or equivalently any PDE that contains p and q, where p is dou z by dou x and q is dou z by dou y. Let us go to the examples. Example 1, form the PDE given Lx plus my plus nz equal to f of x square plus y square plus z square. If you try to relate this to the expression here, you can see that it is of the form u equal to f of v, where u is Lx plus my plus nz and v is x square plus y square plus z square. Now, my friends, how to eliminate the function f? It can be done by just differentiating the given expression partially with respect to both x and y. So, first differentiating the given expression partially with respect to x and y, we get. Now, as you observe, Lx plus my plus nz, when differentiated with respect to x, there is a x term here. So, this will give you L, y is a constant. So, this is 0 and the derivative of nz is n into dou z by dou x, because z depends on x and y. So, I have L plus n into dou z by dou x, which is what is shown here, is equal to, how to differentiate the function f. So, before that, before this expression, you will differentiate the function f, which will give you f dash x square plus y square plus z square. So, how will the derivative be? First, Lx plus my plus nz with respect to x will be L plus n dou z by dou x equal to f dash x square plus y square plus z square into x square plus y square plus z square with respect to x will give you 2x for x square plus z square is 2z into dou z by dou x, or using the notations L plus n into dou z by dou x is p, becomes, here it should be f dash x square plus y square plus z square into 2 times 2 common here x plus zp. Similarly, when you differentiate with respect to y, Lx plus my plus nz, this is the y term. So, that will give you m, and nz should give n into dou z by dou y is equal to, here again f dash x square plus y square plus z square into x square plus y square plus z square with respect to y will be y square is 2y plus z square is 2z into dou z by dou y, because you are differentiating with respect to y. So, if you use the notations, now m plus n dou z by dou y becomes m plus n q equal to, here on differentiation you have f dash x square plus y square plus z square into, take the common factor here, you get 2 times x plus, since dou z by dou y is q, you get 2 times y plus z into q, that is y, okay, with respect to y. So, how to form the PDE? The aim is to eliminate the function f from the given relation. So, just divide equations 1 and 2. What happens if you divide equations 1 and 2? You can see that the f dash terms cancel and also the 2 here cancels, which will give you the relation. Dividing equations 1 and 2, you get L plus NP divided by m plus nq equal to 2 times, this 2 also cancels, f dash will be f dash also will cancel when you divide directly. So, it is x plus zp by y plus zq. Simplify by cross multiplying. So, you have L plus np into y plus zq is equal to m plus nq into x plus zp. Rearrange, multiply the LHS terms, you get Ly plus LZQ plus NYP plus NZPQ is equal to Mx plus MZP plus NXQ plus NZ into PQ. Observe friends that these terms cancel and rearrange. Rearrange by taking all small p and small q terms to LHS, small p small q terms to LHS and remaining terms in the RHS. So, what we do? Shift MZP to LHS, NXQ to LHS, and here the term not containing p or q is Ly shifted to the RHS. So, we get NYP, this will come here minus MZP plus LZQ, this term will come to LHS minus NXQ equal to, already there is Mx, this Ly comes to RHS, which is Mx minus Ly. So, that finally, these two terms have p common. So, you have Ny minus Mz into p plus these two terms have q common, you get Lz minus Nx into q equal to Mx minus Ly, which is the required PDE. Observe that this PDE contains only p and q and hence it is a PDE of order 1. Now, there is one observation to be made. It is convenient to express the PDE obtained in the form PP plus QQ equal to R, like this. So, if you call this as capital P, this as capital Q and this as capital R, it is PP plus QQ equal to R, where PQ R are functions of x, y and z. This is called the Lagrange's linear equation. Now, friends, we will go to the next example. Now, eliminate the function f from the relation x, y, z equal to f of x plus y plus z. Now, the method remains the same. Differentiate, because there is one function f to be eliminated, again it is a PDE of order 1. So, differentiate these expressions partially with respect to x and y. So, when you differentiate with respect to x, in x, y, z, y is a constant. So, write it outside and apply product rule for x and z. So, what is the product rule for x and z? It is x into first function x into z is dou z by dou x. So, it is x into dou z by dou x plus second function z into x is 1. So, that is what you see, friends, here. equal to RHS, first differentiate f like you have seen in the previous slide, differentiate the function f that was shown written in the presentation. So, first f becomes f dash of x plus y plus z into x plus y plus z with respect to x is 1 and z is dou z by dou x. So, if you use notations, this will be y into xp plus z equal to f dash x plus y plus z into 1 plus p. Similarly, differentiating partially with respect to y in the LHS in the product x y z, x is a constant. So, take it outside, apply the product rule for y and z. So, that will give you x into y times the derivative of z with respect to y is dou z by dou y plus z into y is 1. That is what you see here, equal to f of x plus y plus z is f dash of x plus y plus z into x plus y plus z with respect to y is 1 for y and z is dou z by dou y. So, if you apply notations, this is x into yp plus z, sorry, yq plus z equal to f dash x plus y plus z into 1 plus q. So, as in the previous example, just divide the two expressions. So, dividing equations 1 and 2, you can see friends that this will cancel. The same thing happened in the previous example also, f dash terms will cancel. So, left hand side will be y into xp plus z by x into yq plus z equal to 1 plus p by 1 plus q. Simplify by cross multiplying. So, y into xp plus z into 1 plus q will be equal to x into yq plus z into 1 plus p. Multiply term by term, the LHS will give xyp plus xypq plus yz plus yzq equal to xyq plus xypq plus xz plus xz into p. Notice that xypq terms cancel, take all p and q terms to LHS, remaining terms take to RHS. So, you get xyp, this p will come here, minus xzp plus yzq, this q term to LHS is minus xyq equal to xz which is already present, then yz on this side goes to RHS to give you minus yz. So, that finally, the required PDE of order 1 is, in this you have x and p common. So, it gives you x into y minus z into p plus y into z minus x into q equal to z into x minus y, which is again a PDE of order 1. Now, let us go to the next example. In this example, you will see the differentiation using the quotient rule. Now, eliminate the function phi from the relation z is equal to phi of x y by z. So, the differentiation process is again the same. You will differentiate because there is one function to be eliminated, you will differentiate partially with respect to x as well as y. So, first differentiating z with respect to x, I get dou z by dou x which is p, RHS phi of x by x z first becomes phi dash x y by z, and then in x y by z you should differentiate partially with respect to x. So, in x, y and z, y is a constant which you see friends is written outside. Then apply quotient rule for x by z. So, when you apply quotient rule for x by z, first it is denominator square z square, then denominator z into differentiation of numerator x is 1 minus numerator x into derivative of z is dou z by dou x. So, if you apply notations, this will be p. So, you get z minus xp by z square. Similarly, when you differentiate partially with respect to y, dou z by dou y equal to q will be first phi of x y z is phi dash of x y z, and then x y by z with respect to y will mean x is the constant which is outside. Apply quotient rule for y divided by z. So, when you apply quotient rule for y divided by z, first denominator square z square, then z into differentiation of y is 1 minus y into differentiation of z in the denominator is dou z by dou y, which is, as you know friends, is q by notation. So, we are left with phi dash of x y by z into x into z minus y q by z square. So, as we did in the previous two examples, just divide these two expressions for the required PDE. So, dividing equations 1 and 2, we get left hand side you have p and q. So, p by q, right side phi dash term cancels, these two are separate terms, you get y by x into this expression. When you divide these two expressions, the denominator z square term cancels, leaving you z minus xp in the numerator and z minus yq in the denominator. That is written here. Cross multiply px into z minus yq is equal to qy into z minus xp, or xzp minus xypq is equal to yzq minus xypq, cancel xypq and remove the common factor z on both sides to give xp equal to yq, or xp minus yq equal to 0 is the required PDE. Now, these examples related to the expressions of the form u equal to f of v. Now, let us look into the examples where the given expression is in the form f of u comma v equal to 0, where f is the arbitrary function and x, y, z are functions of, u and v are functions of x, y and z. What is the aim? To eliminate the function f, which will result in a PDE of order 1. So, again the PDE will contain only p and q. Now, these examples in particular require some theory part to be written. Okay. Now, the exact procedure for the theory part is shown in the next slide. So, by data it is given f of u comma v equal to 0, correct. So, differentiating partially with respect to x and y, apply chain rule for this. What is chain rule? F of u v equal to 0 becomes, with respect to x, dou f by dou u into dou u by dou x plus dou f by dou v into dou v by dou x equal to 0, or dou f by dou u into dou u by dou x will give, shift this to RHS. When it goes to RHS, you get dou f by dou u by dou x equal to minus dou f by dou v into dou v by dou x. So, let us call that expression 1. Similarly, using chain rule, now differentiate partially with respect to y. So, you get similar to the differentiation with respect to x above in equation 1, dou f by dou u into dou u by dou y plus dou f by dou v into dou v by dou y equal to 0, or again keep this in LHS, shift this to RHS, you get dou f by dou u into dou u by dou y equal to minus dou f by dou v into dou v by dou y. So, again divide equations 1 and 2. So, in the LHS this will cancel. So, you can see the division shown here. So, this will cancel. In the RHS, the negative sign as well as dou f by dou v will cancel, leaving you dou u by dou x by dou u by dou y equal to dou v by dou x divided by dou v by dou y, or on cross multiplication you get dou u by dou x into dou v by dou y equal to dou u by dou y into dou v by dou x. So, what you see in the procedure is the following. Through a differentiation sequence, in this process itself, you have eliminated the function f, so that finally you are left with only the 4 partial derivatives dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y. These 4 partial derivatives when substituted in this relation will give you the required PDE. So, just substitute and rearrange. Now, you can see friends that when you practice this relation here is equivalent to the previous 3 examples. That is to say, u equal to f of v and f of u v equal to 0 are equivalent problems. Both will give you the same PDEs. Now, when we solve examples in this, in the slides that we continue now, we will directly start with f of u v equal to 0, identify u and v. Okay. Then this procedure shown that you see in the slide now up to equation 3 will not be repeated in the problems. Let me remind you friends that this should be shown when you, this should be derived when you solve. So, you start with u v, come to equation 3 first and then solve the PDE. Let us go to the first example. Form the PDE by eliminating the arbitrary function f from the relation f of x plus y plus z, comma x square plus y square minus z square equal to 0. Now, you can try friends, you try to express the same example like this, f of, that is, if this is, take the first function on the left side, call that u and write it as f of x square plus y square minus z square. You will see that if you apply the previous method, you come back to the same PDE. The PDE obtained by this method as well as the PDE obtained from the previous method are one and the same. Now, let us follow the method illustrated now. Given f of u v equal to 0, the first function is u. So, u is x plus y plus z and v is x square plus y square minus z square. You can see this clearly written. Repeat the derivation up to equation 3 that is that was shown in the previous slide. For easy reference, I will just show you the previous slide again. So, you start with f of u comma v equal to 0, apply chain rule, differentiate partially with respect to x first, then differentiate partially with respect to y first, then obtain these expressions by shifting the second term to the RHS, then divide the two expressions which will cancel dou f by dou u and dou f by dou v, and finally cross multiply to get this relation dou u by dou x into dou v by dou y equal to dou u by dou y into dou v by dou x. As you see, we have written here, consider the expression dou u by dou x into dou v by dou y equal to dou v by dou x into dou u by dou y. Now, when you find out these partial derivatives, you must remember that even though u is a function of x y z and v is a function of x y z, the variables x y z are related in such a way that z depends on the variables x and y. So, to find these 4 derivatives, we go to equation 1 first, differentiating equation 1 partially with respect to x and y, we get first u equal to x plus y plus z gives you dou u by dou x on the left side, right side x is 1, y is 0 and z is dou z by dou x, that is what is written here. So, I get 1 plus 0 plus dou z by dou x, which is equivalent to 1 plus p. Then, when you differentiate with respect to y, x is 0, y is 1, z is dou z by dou y, which gives dou u by dou y equal to 0 plus 1 plus dou z by dou y, which is 1 plus dou z by dou y also equal to 1 plus q. Now, go to the expression in equation 2 and differentiate partially with respect to x and y. So, differentiating equation 2 partially with respect to x and y, we get first dou v by dou x, x square is 2x, y square is 0. What is z square, friends? Because z depends on x and y, z square will be first 2z followed by the corresponding partial derivative dou z by dou x. So, that if you take 2 common and use notation, it is 2 times x minus zp. Similarly, dou v by dou y will be x square is 0, y square is 2y. What about z square again? Because z depends on x and y, z square is first 2z followed by dou z by dou y, because you are differentiating partially with respect to y. So, you will get 2y minus 2z into dou z by dou y, or it is 2 times y minus zq. Now, these 4 partial derivatives are directly substituted in this equation. Let me remind you, friends, the derivation should be shown. You should show how you arrive at equation 3. So, substituting these expressions in equation 3, you get 1 plus p for dou u by dou x into dou v by dou y is 2 times y minus zq equal to dou v by dou x is 2 times x minus zp into dou u by dou y, which is 1 plus q. So, you have that relation there. First, cancel the 2 on both sides, this 2 will cancel, then multiply across, you get y minus zp plus py minus pqz equal to x minus zp plus xq minus pqz. Cancel pqz terms, and as we did in the previous type, take all p and q to LHS, terms not having p and q bring it to RHS. So, you get minus zq plus py, this will come minus zp here will become plus zp, then plus xq to LHS will give minus xq equal to x is already present, these terms have gone to LHS, this term comes to RHS as minus y. Then finally, if you take common factors, these two have p common, so you get y plus z into p, these two terms have minus q common, so take it out. So, minus of z plus x into q equal to x minus y, which is the required PDE. Let me remind you again, if you try to solve this problem using the previous method, you will get the same answer, because these two are equivalent. Now, again it is convenient to express the PDE obtained in the form PP plus QQ equal to R, which we earlier said as the Lagrange's linear equation. Now, let us go to the next example. Eliminate the function f from the relation f of xyz comma x square plus y square minus 2z equal to 0. As you see, friends, again this relation is in the form f of u comma v equal to 0, where u is the first expression xyz, v is the second expression x square plus y square minus 2z. Make a note of this, repeat the derivation up to equation 3, which was dou u by dou x into dou v by dou y equal to dou u by dou y into dou v by dou x. By the usual process, apply chain rule and show the derivation coming up to equation 3. Now, again like in the previous example, observe that this expression does not contain f. You have already eliminated the function f, leaving out the 4 partial derivatives of u with respect to x and y and v with respect to x and y. So, first let us differentiate equation 1 partially with respect to x and y respectively. In the LHS, as was illustrated in one of our previous examples, with respect to x, y is a constant that will stay outside. Apply product rule for x into z, which will give you x into dou z by dou x plus z into 1, which is this. When you apply the notation, it is y times xp plus z. When you differentiate partially with respect to y, x is the constant which will stay outside. Apply product rule for y and z. So, it is y into dou z by dou x plus z into 1, which on using notations becomes x times yq plus z. Now, differentiating this partially, the expression v with respect to x and y respectively, first x square is 2x, y is 0, minus 2z changes to minus 2 dou z by dou x, or when you take 2 common, it is 2 times of x minus p. Similarly, dou v by dou y is equal to 2y minus 2z, 2 into dou z by dou y, which is 2 times y minus q. Again, we will take these 4 expressions and substitute in equation 3 and simplify for the required PDE. So, that is shown in the next slide. Substituting in equation 3, we get dou u by dou x into dou v by dou y equal to dou u by dou y into dou v by dou x. Cancel 2 and rearrange. So, I get x y p plus take this y inside x y p plus y z into y minus q equal to, write this x inside x y q plus x z into x minus p, multiply term by term to get this and do the cancellations whichever is relevant. These 2 terms cancel, shift small p and small q terms to LHS, shift the term not containing p or q to RHS, which will give you this x y square p minus y z q, this comes here, minus x square y q plus x z p equal to x square z, this y square z goes to RHS as minus y square z, or finally taking p and q terms to LHS, we are left with x into y square plus z into p minus y into x square plus z into q equal to z into x square minus y square, which is the required PDE again of order 1. Let us move on to the next example. Form the PDE by eliminating the function f from the relation f of x square plus 2yz comma y square plus 2xz equal to 0. Again, this relation is in the form f of u comma v equal to 0. Let me remind you, you can also, because it is equivalent to u equal to f of v, the answer should be one and the same. U is x square plus 2yz, v is y square plus 2xz. Repeat the derivation up to equation 3, which was shown in one of our previous slides, which will give you these 4 partial derivatives. So, differentiating equation 1 partially with respect to x, we get dou u by dou x will be x square is 2x in 2yz, 2 and y are constants, keep it aside, z with respect to x is dou z by dou x, using notations it reduces to 2 times of x plus y into p. Then differentiating partially with respect to y, similarly dou u by dou y. Now observe, you have x square plus 2yz, correct. So, when you differentiate with respect to y, x square is a constant. So, that becomes 0, no differentiation for that because derivative of a constant is 0. So, that term becoming 0, you are left with 2yz in which y and z are both variables. So, apply product rule to yz. So, it is 2 times y into derivative of z is dou z by dou y plus z into 1. Okay, friends, apply product rule for y into z. So, that you are left with 2 times y cube plus z. Similarly, go to the expression for v in equation 2 and differentiate partially with respect to x and y. Now, as in the previous case, when you differentiate with respect to x, v with respect to x, y is a constant which is 0. You are left with only the expression 2xz, for which you need to apply the product rule. So, if you apply product rule, so you have 2 into x into z, 2 comes out as the constant, apply product rule for x into z, which gives you x into dou z by dou x plus z into 1, which on using notations is 2 into xp plus z. Now, as far as dou v by dou y is concerned, because v is y square plus 2xz, y square is 2y, and in 2xz, 2 and x are constants, leaving you with the derivative of z as dou z by dou y, which is 2 times y plus x into q. Again, substitute that in equation 3, dou u by dou x into dou v by dou y equal to dou u by dou y into dou v by dou x, which gives you this expression. So, cancel 2 into 2 4 on both sides and then multiply across, cancel the terms which are equal terms and shift PQ terms to LHS, terms not containing PQ to RHS to get you finally this expression y square minus xz into P plus x square minus yz into q equal to z square minus xy, which will be the required PD. Let us go to the next example, which is again similar to the previous 3 examples. In this example, u and v are x square minus xy and x by z respectively. You need to eliminate again the function f. So, differentiate u with respect to x and y. So, dou u by dou x is 2x minus y, dou u by dou y is minus x. You should be careful when you do dou v by dou x because v is x by z. So, you should apply quotient rule, first denominator square z square, then z into differentiation of x is 1 minus x into differentiation of z is dou z by dou x, that is seen here. Use notations to get z minus xp by z square. Now, when you differentiate with respect to y, you should be careful because with respect to y, x is constant. So, that will stay out. Derivative of 1 by z is minus 1 by z square, followed by the partial derivative of z with respect to y, which is dou z by dou y, and that gives you minus x cube by z square. Again, all the 4 derivatives here are substituted in equation 3, which gives you the expression here 2x minus y into minus x cube plus by z square equal to minus x into z minus xp by z square. Cancel z square, cancel the negative sign, rearrange to get the final PD as x square p plus x into 2x minus y into q equal to x into z. As you see, friends, all the examples follow a common method. The only thing is that you should do the differentiation process correctly, identify the correct variables and do the differentiation either with respect to x or with respect to y. In the next example, the function to be eliminated is phi. So, eliminate the function phi given phi of x y by z comma x minus y by z equal to 0. So, you are given phi u v equal to 0, where u is x y by z and v is x minus y by z. So, you repeat the derivation up to equation 3 again. The derivation shown in the one of the previous slides was related to the function f. So, it is quite obvious that to show the derivation you just replace f by phi and arrive at equation 3 again. Now, how to differentiate? Because u is x y by z, when you differentiate u with respect to x and y partially, with respect to x, y is a constant which will be outside, apply quotient rule, it was illustrated in our previous slides. So, you get z minus x dou z by dou x by z square. When you differentiate with respect to y, x is constant, apply quotient rule for y by z to get you dou u by dou y equal to this. Then, when we find dou v by dou x again, v is x minus y by z. So, you require quotient rule for both dou v by dou x as well as dou v by dou y. For dou v by dou x, first it is denominator square z square, then denominator z into differentiation of x minus y is 1 minus numerator x minus y into differentiation of the z is dou z by dou y, which will give you z minus of x minus y into p by z square. Similarly, if you apply quotient rule for x minus y by z and differentiate with respect to y, you get dou v by dou y as denominator square z square, then z into differentiation of x minus y is minus 1 with respect to y, minus x minus y into derivative of z is dou z by dou y. Using notations, you get this. Now, again you substitute this in equation 3 to get this expression y into z minus xp by z square. This is dou u by dou x into dou v by dou y equal to dou u by dou y into dou v by dou x. Cancel the z square and multiply across. First I have taken this y and multiplied to this, take x and multiply to this, rearrange, multiply the left hand side terms and right hand side terms and remove the terms which are equivalent, cancel the terms which are equivalent. You can see that x y z p cancels, then x y z q here as well as here cancel. Okay, rearrange by taking all p and q to LHS, remaining terms to RHS to give you this expression. Or finally, z into x square plus p, x square into p plus y square q equal to z square into x plus y. Again cancelling z on both sides, so you get x square p plus y square q equal to x plus y, which is the required PDE. Now, there is a similar example which can be practiced at your end. Eliminate the function phi, these are u and v, follow the same process to arrive at the PDE 2z minus x into p plus y minus 2z into q equal to x minus y. Now, I end this lecture with a few practice problems which are on display. So, friends, in today's session we have seen the formation of a PDE by the elimination of a single function f from two types of relations. First, when the relation is in the form u equal to f of v, and the second when the relation is in the form f of u comma v equal to 0. So, in the problems that you see which are displayed, the first 5 examples are those in the type f of u comma v equal to 0. Only thing is the function varies, in some it is phi, in some it is g, and the last 3 examples for practice are those in the form u equal to f of v. Thank you.